everyone, thank you so much for clicking onto the video. Today we're going to be looking at extending carbon chain length. So we're going to look at the use of carbon-carbon bond formation in synthesis to increase the length of a carbon chain, and the formation of this CCN by reaction of haloalkanes with a CN- and ethanol, including nucleophilic substitution mechanism, carbonyl compounds with hydrogen cyanide, including nucleophilic addition mechanism, and the reaction of nitriles from B by reduction with hydrogen and nickel to form amines, by acid hydrolysis to form carboxylic acids. And then finally, we're going to look at the formation of a substituted aromatic carbon-carbon single bond by alkylation and acylation in the presence of a halogen carrier. So now we're going to look at carbon-carbon bond formation. Forming carbon-carbon bonds in a reaction is very important as we can synthesize new compounds containing more carbon atoms. And there are a few ways in which we can extend the carbon chain, and we're going to look at 4 of these reactions. So the first is when we form nitriles from haloalkanes, and then we're going to look at forming nitriles from carbonyl compounds, so aldehydes and ketones, so the compounds with this C double bond O group. And then we're going to look at Friedel-Crafts alkylation and acylation of aromatic compounds. So in particular, we're going to look at benzene. And these are both in the presence of an aluminium chloride catalyst. So the first reaction we're going to look at is forming nitriles from haloalkanes. And this is a nucleophilic substitution reaction, and where CN- will act as a nucleophile, and this will substitute the halogen in the haloalkane. So the reagent we use is potassium cyanide in ethanol or sodium cyanide. And so the nucleophile acting is the CN-. And so we're going to look at the reaction of 1-chloropropane and potassium cyanide. So I'm going to draw out 1-chloropropane. So we have CH3, CH2, and then a carbon with 2 hydrogens, and then a chlorine. And so because chlorine is much more electronegative, we have partial charges. So we get a partially positive charge on the carbon and a partially negative charge on the chlorine. And it's this partially positive carbon which attracts the nucleophile because it has a spare pair of electrons. So we have the nucleophile here, which is a CN-, and we have a spare pair of electrons. And so these 2 electrons are attracted to this partially positive charge on the carbon, and so they attack it. And then what happens is that the electrons from this bond here between the carbon and the chlorine move towards this chlorine, and we get this nucleophilic substitution reaction. And so what we form, CH3, CH2, CH2, and then now we have a cyanide attached. And we also have the Cl-, which has been substituted out. So the product we have is butane nitrile. And as you can see, we have 1 extra carbon. So in this nitrile, we have 4 carbons, whereas in the haloalkane, we only have 3. So we've extended the carbon chain by 1 by going through this nucleophilic substitution reaction. And so overall what we have is CH3, CH2, CH2Cl, added with some potassium cyanide will form this butane nitrile. So CH3, CH2, CH2CN, and then we'll have potassium chloride as the byproduct. So the second reaction we have is when we form nitriles from carbonyl compounds, and these are nucleophilic addition reactions. So again, this CN- will act as a nucleophile, and it's added onto the delta positive carbon in this CO double bond, and a hydrogen is added onto the delta negative oxygen. And so what we form are hydroxynitriles. So nitriles where we also have an OH group. So the reagent we use is sodium cyanide or potassium cyanide mixed with some sulfuric acid. And the nucleophile is the CN-. So we're going to look at the reaction of propanone and hydrogen cyanide. So hydrogen cyanide is actually too poisonous to use on its own, and that's why we have to mix either sodium cyanide or potassium cyanide in some sulfuric acid, because the sulfuric acid will provide that H+. And so what we have is, firstly, drawing out propanone, we have CH3, C double bond O, and then CH3. And so we have a delta positive charge on the carbon because oxygen is much more electronegative. So the oxygen will have the partial negative charge. And then we have our nucleophile, so this Cn minus with the spare pair of electrons. And these electrons are really attracted to this partially positive carbon, and so they move towards this carbon and attack it. And then what happens is that the electrons from this bond then move towards this oxygen. So what we form is CH3, and then we've got a carbon and an oxygen, and now we have a spare pair of electrons on this oxygen. So this oxygen is now negatively charged. And then we also have the cyanide and a CH3 group now attached. And now we have a H plus from the acid, the sulfuric acid. So H plus attacks, and this is from the solvent. And this is attracted to the 2 electrons on this oxygen with the negative charge. And so what happens is that this H plus then attacks this oxygen, and then we can form our hydroxynitrile. So we have CH3 and then COH, CH3, and then the cyanide. And so again, we can see that we've added another carbon. So we started off with 3 carbons, and now we have 4. And the overall equation is this propanone, so CH3, COCH3, reacts with hydrogens to form CH3, COH, CN, CH3. We also need to know about the reactions of nitriles. So just to remind you, the nitrile is just a compound with a C triple bond N. So it's got this attached somewhere onto the compound. And so the 2 reactions of nitriles that we need to know is firstly the reduction of nitriles. So nitriles can be reduced to amines, and we do this by reacting it with hydrogen in the presence of a nickel catalyst. So for example, if we're going to look at the reduction of propane nitrile, first we start off with this propane nitrile, so CH3, CH2, and then C triple bond N. And if we add some hydrogen with some nickel catalyst, then what we would form would be CH3, CH2, CH2, NH2. And so this means that we would need 2 of these hydrogens. And what we formed is propylamine. So we basically added hydrogens onto the carbon and the nitrogen of this CN bond. And the second reaction we have of nitriles is the hydrolysis of nitriles. So nitriles undergo hydrolysis to form carboxylic acids by heating them with dilute aqueous acid. So for example, the hydrolysis of butane nitrile would look like this. We would have CH3, CH2, CH2, C triple bond N, and then we would add some water and also some HCl, which is aqueous. And then by heating this, what we would form would be butanoic acid. So we'd have CH3, CH2, CH2, and then COOH. And we'd also form a salt. So we'd have NH4Cl. So this is butanoic acid. Now we're going to have a look at the alkylation of benzene. So this is one of the methods we can use to add more carbons onto aromatic compounds. So in the presence of an aluminium chloride catalyst, benzene will react with haloalkanes to form alkyl benzenes. So just benzenes with an alkyl group. And this is an example of an electrophilic substitution reaction. And the reagent we use is a haloalkane in the presence of an aluminium chloride catalyst, and the electrophile is the RCH2 plus group. So for example, looking at the ethylation of benzene, the haloalkane we're using is some kind of haloethane. So for example, if we used some chloroethane, what we would get would be the benzene reacting with some chloroethane. So we have CH3, CH2, Cl, and this will react in the presence of this aluminium chloride catalyst. And this will form benzene with this newly attached CH2, CH3, and what is removed is HCl, because we removed a hydrogen from the benzene, and this will react with the chloride that's been taken away, well substituted out of this chloroethane. And so what we've formed is ethyl benzene. So in this case, our electrophile is this CH3, CH2 plus ion. This is our electrophile. And as you can see, we've added some more carbons onto this aromatic compound. And the last reaction we have, which extends the carbon chain, is the acylation of benzene. So in the presence of an aluminium chloride catalyst again, benzene will react with an acyl chloride, so this is an acid derivative, to form an aromatic ketone, so a ketone with a benzene ring. And this is an example of an electrophilic substitution reaction again. And the reagent we use is an acyl chloride in the presence of an aluminium chloride catalyst, and the electrophile is this RC double bond O plus ion. So for example, in the acylation of benzene to form phenyl, so we start off with some benzene, and then we're going to react this with some propanoyl chloride. So that's just for this example. So we have CH3, CH2, and C double bond O, Cl. And we know that we have to use propanoyl chloride because the product is phenylpropanone. And so in the presence of an aluminium chloride catalyst, what we form is the benzene ring, but this time we have a C double bond O, and then we have CH2, CH3. And this is our phenylpropanone. And we also form HCl. And this is because we've taken off a hydrogen off this benzene ring and reacted it with the chlorine from this propanoyl chloride. So again, we can see that we've extended the carbon chain.